This is section 2C, part 2. So we've looked at a shortcut for really polynomials, powers of x. I'd like to also look at a couple of other shortcuts for some trig functions and exponential functions. For right now, we're going to stick with just sine and cosine. We'll do sine and then we'll kind of assume cosine from there. So I'd like to once again go back to our definition of the derivative and see if we could figure out what the derivative is when our function is sine x. So we would have the limit, as h goes to 0, of the sine of x plus h minus the original function, sine x, over h. Now we need to simplify this somehow, because there's certainly a 0 in the denominator right now, which is a problem. Trig functions are particularly difficult to work with in terms of manipulating them, right? Usually you can't just sort of break apart things in a trig function or pull things out of a trig function. The only way to really manipulate a trig function is to use a trig identity. So that's what I'm going to try and do here. This sine of x plus h. If you look at the list of formulas that is part of your course pack, one thing that you have is a whole list of trig identities. And I'm looking right now at this sum and difference identity that says the sine of a plus b is sine a cosine b plus cosine a sine b. I'm going to use this, but instead of a and b, of course, I have x and h. So I'm going to say this is, the limit as h goes to 0. And then using the trig identity on the sine of x plus h, I would have sine x cosine h plus cosine x sine h. All right, we'll put in the rest of our difference quotient here, so I'd have a minus sine x, and then the h in the denominator. All right, usually this is where we say, hey, this is great because things start to cancel out and all that stuff. But unfortunately, I did not have that happen this time, right? There's nothing that makes a 0, nothing I can really do yet. So I'm going to break this up into two separate limits. I'm going to say, notice that sine x is part of the first and last terms. So I'm going to take those two and make them one limit, and then I'm going to add this as a second limit. So I would have sine x cosine h minus sine x, all the parts that have sine in them, or sine x in them anyway, over h, plus this middle term, I'm separating that out as its own limit. And I'm adding, so I do have to have the common denominator for both of them. All right, starting to see the light at the end of the tunnel here. If I were to factor out the sine x from this numerator, what I'd have left is cosine h minus 1 over h. And that's starting to look a lot like one of those special limits that we studied. We'll go back and take a quick look at it on the sheet, but I'm feeling pretty good about that. I have the same sort of situation going on here. If I just kind of pull the cosine x out as a separate factor and say it multiplies sine h over h, that also looks like one of those special limits that we've studied. By the way, that list of special limits is also in your list of formulas that you're allowed to use when you take tests, midterms, finals, and so on. And let's see what we've got here. This one is almost the same as that one, right? Now I will notice that 1 minus cosine x, and this is cosine h minus 1, it's reversed. But that's really just a multiplier of negative 1. And if I multiply 0 by negative 1, it's still 0. So I think I'm okay with that one. This is sine x times that special limit of 0. plus cosine x, and the sine h over h as h goes to 0, that's another special limit. That's this one right here, right? And that becomes 1. So when all is said and done, I'm just going to get cosine x. For my derivative. So my conclusion is that if f of x is sine x, then f prime of x is cosine x. You can use an almost identical procedure to find the derivative of cosine x, and in fact I believe that's one of your classwork assignments coming up, so I'll just say use this as a model because the process is very, very similar. And I'm going to tell you, you should get the opposite of sine x when you do that. So going forward, we will now say that these are known limits. We can use the shortcut forms. We just already know what the derivatives are. And we'll use them in more complicated derivatives in just a little bit. One more new one for today before we just start combining what we already know. Let's take a look at the exponential function. What if f of x is e to the x? Well, if I wanted the derivative, then f prime of x would be the limit as h goes to 0 of e to the x plus h minus e to the x over h. We're back in a situation where we don't have an obvious simplification, so we're going to have to do a little bit of work with this one. One thing that I do see that I could do right away is factor out an e to the x. So let's at least do that much. That's going to make the first term e to the h, right? Because if you multiplied, you'd add those exponents and be right back where you started. Minus 1 over h. E to the x itself is no problem because we're looking at h going to 0. So e to the x is just going to stay e to the x. It's the rest of this that I have to deal with. And once again, at this point, I'm not in a situation where I can easily see something that I'm going to be able to get rid of, no terms cancel out, nothing like that. So I'm going to have to dig a little deeper. So let's see here. This e to the x, I'm just going to say this is fine, and e to the x times the rest of it. It's the rest of it that's the problem. And I'm going to actually do something here. It's going to look like I'm making a great big mess, but I promise you, hang in there, it's going to get better. What I'm going to do is I'm going to write e in a very, very complicated way. It's another one of our special limits. In our case, we have h going to 0, so I could actually write e as 1 plus h to the 1 over h power, and that limit is e. So let's do that. I'm going to replace this e with 1 plus h to the 1 over h power, because the limit of that as h goes to 0 is e. So all of this is just the e. Now that e was supposed to be raised to an h power, so I'll do that. And then minus 1 all over h. And like I said, I know it looks like I made a simple situation much worse, but there's now algebra that I can do. Right? When you raise a power to a power, you multiply the exponents. And 1 over h times h is just a first power, right? So what I've got here is the limit as h goes to 0 of e to the x times 1 plus h to the first, or just 1 plus h, minus 1 over h. And that just got a lot better. 1 minus 1 is 0, and then of course h divided by h is just 1. So this is e to the x times 1, or simply e to the x. So if f of x is equal to e to the x, then f prime of x is also e to the x, the only function that is its own derivative. This one we also had a little bit of a hint on when we looked at the derivatives graphically. Remember this graph? The one where we had said it looked like the derivative would follow the graph of the original function perfectly? This really is the graph of e to the x, right? This is an exponential growth function. You could even say with the first power here, we're right about 2.7 or right about e. So in fact, it is true that when we've got e to the x, that function is its own derivative. There's a slight variation when we have a base that's not e. If we've got some number a to the x power, the derivative is still a to the x power. But we also have to have a little bit of a fudge factor, so to speak, to account for the fact that we have a different base. We end up having to multiply this by natural log of a. The reason for that is something that I can't quite get to yet because we don't quite have another rule that we'll eventually get and we'll need. But for now, I'm just going to ask you to accept that as the rule for taking the derivative of a to a power. So before we put all of our rules together in some combination problems, I'd like to just say a word about notation. There are actually four different notations for the derivative that you may come across in your mathematical or possibly physics careers, and I wanted to mention them here. First of all, Newton, one of the earliest inventors of calculus, uses a dot for the derivative. So if we've got a function y equals f of x, he would have written the first derivative as simply y with a dot above it. Typically Newton, because he was primarily interested in calculus as a way to help him with physics, was taking derivatives with respect to time. And you'll still see this dot notation occasionally used, particularly in physics books, where all the derivatives are usually time-based derivatives. So used mainly for functions of time. Leibniz notation. In the Leibniz notation, he would have written the derivative dy dx, so the derivative of y with respect to x. Notice that this is a nice notation because it doesn't presuppose that t is our independent variable, and it actually allows us to declare both the dependent and independent variables right within the notation. It's also very reminiscent of the idea of slope. So it kind of reminds us of the fact that the derivative really is just the slope of the tangent line, right? Slope was delta y, the change in y, over delta x, the change in x. And this is just the calculus for the derivative, dy dx, or the instantaneous slope, or slope of the tangent line. This one gets used a lot. We will definitely use Leibniz notation when we do derivatives. Euler notation is the next one, and if we have y as a function of x, the Euler notation would have looked like this. The derivative of y with respect to x. Again, notice an advantage is that, like Leibniz, we have the opportunity to state both the dependent and independent variable, but it's not quite as reminiscent of the slope. Finally, Lagrange. This is the one we've actually been using, and we'll continue to use it. Y prime, or possibly f prime of x, would be the way the Lagrange notation for the derivative would look. The only real disadvantage of this is that if you just put y prime, it doesn't give you the advantage of being able to know what the independent variable was. If you use f prime of x, it does. All right, I will mainly use these two, and I'll try to mix them up a bit so we get used to them. But let's go ahead and finish out this section with some combination problems. We will be relying on some arithmetic rules for derivatives, and notice that some of these are going to look very similar to the limit rules that we learned. If you have the sum or difference of two functions, you can just find the derivative of each term separately and add or subtract to get your final answer. If you have a constant multiple of a function, that constant multiple can get pulled out, just like we did with the limits, and you can have that constant times f prime of x. I will mention, notice what you don't see here. There's nothing here that says that the derivative of a product is just f prime times g prime, and in fact it's not. There's nothing that says the derivative of a quotient is just f prime over g prime, and again, it's actually not. So we will look at those rules for products and quotients as we go forward in the next section. But for right now, we have just these three rules that we can use. So let's try them out. I would like the derivative of this polynomial function, and it's just the sum and difference, so I can treat each term separately. And I'm going to say f prime of x. I would have the multiplier 7 times the derivative of x cubed. I can use my power rule, 3 times x squared, minus constant multiplier of 6 times the derivative of x squared, 2x to the first, plus, that's just a linear term, slope would be 4, so the derivative is 4, and the derivative of a constant term is 0. So I end up getting 21x squared minus 12x plus 4. Now I will mention that usually as you get kind of comfortable with this, most people sort of skip this intermediate step and they start saying, well, I can tell that when I bring this 3 down as a multiplier, it's just going to multiply the 7. So they end up just thinking 3 times 7 is 21 and reduce the exponent by 1. 2 times 6 is 12 and reduce the exponent by 1, etc. So using that shortcut is just fine. I'm sure I will in a little while as well. Number 2, before I actually start taking a derivative here, I'm going to rewrite these so they look like powers of z. So careful with notation here. This is still w. I'm not doing a derivative yet. I'm just rewriting this as 4z to the 1/3, subtract 5z to the negative 2. All right, let's do a little Leibniz notation here. W is the dependent variable, and z is the independent. So if I was going to use Leibniz notation, this would be dw dz. I have the constant multiple 4, and then the derivative of z to the 1/3. 1/3 z to the 1/3 minus 1 would be negative 2/3. Subtract 5 times, and the derivative of z to the negative 2. Negative 2z to the negative 2 minus 1, or negative 3, which gives me 4/3 z to the negative 2/3, plus 10 z to the negative 3. And again, you're welcome to move factors down to the denominator so you don't have negative exponents, but I find that it's usually easiest just to leave the regular exponential form. All right, we have a few problems on the next page to wrap up our section. In number 3, h of t here is a product. And as I mentioned a few moments ago, we don't have a rule for products. So you will have to multiply this out before taking the derivative. So this is still h of t, not taking the derivative yet. Multiplying that out would give me 3t squared. I'd have 18 minus 2, so plus 16t, minus 12. And now I can take h prime of t. Maybe I'll start shortcut here. 2 times 3 would be 6. And that would just be t to the first power when I reduce the exponent by 1. Plus, that's linear, so the derivative is the slope, 16. And of course the derivative of the constant would just be 0, so I won't even write that. And there's my derivative, 6t plus 16. Number 4, also a form that I cannot take the derivative of right now because it's a quotient. And we only had rules for sums and differences and constant multipliers, right? So I'm going to have to divide first before I take the derivative. So let's do that. Still f of x, I'm just simplifying. I'd have 5/2 and subtracting exponents, x to the second, plus 3/2 x to the first, minus 3, plus this will be a 2x to the negative 2, subtract, and I'm going to write that last one as a 1/2 and then an x to the negative 3 so that I can easily use my power rule. And now I'm ready to do f prime of x. So 2 times 5/2 would be 5, x to the first. This piece is linear, so plus the slope, 3/2. This piece is just a constant, so its derivative is 0. I won't even bother writing that one. Over here I would get negative 4, x to the negative third when I reduce my power by 1. And then negative 3 times negative 1/2, positive 3/2. And reduce that exponent by 1, negative 4. And again, I'm perfectly okay just leaving everything with the negative exponents. That's a perfectly good answer. All right, number 5. Let's do Leibniz here, dy dx, or traditional independent and dependent variables, it looks like. We have the constant multiplier of 8. And then these are those derivatives that we have rules for now. We're just going to go ahead and grab them. Remember these. The derivative of sine x is cosine x. Plus, we have a constant multiplier of 3. And the derivative of cosine x is the opposite of sine x. Now, I don't ask you to do a whole lot of simplifying, but when you have something like this, because later on we'll be using these to work with in larger problems, it is best to do a little simplifying here. You're better off writing this as 8 cosine x, and then just multiplying the 3 times the negative 1. So minus 3 sine x. So those basic simplifications I would like you to do. All right, last one. This would be dy dt for our independent variable. And I've got a constant multiplier of 6. The derivative of e to the t is still e to the t. That exponential function is the only one, again, whose derivative is itself. And the derivative of a constant term, 5, is just 0. So that's done. All right, that brings us to the end of section C.